So if you see the grounding, you know the emitter is grounded through RE parallel to CE, and the midpoint of capacitance is also grounded. Okay, so if terminal 1 is positive, you know that because of common emitter action, terminal 2 is negative. So this 180, again 180, total phase should become 360 degrees. So 1 is common to both the feedback path and the base. 2 is common to both the feedback path and the collector. So whatever polarity appearing across the transistor, the same polarity will be appearing across the feedback path also. So effectively, if you add total phase shift, it will be equal to 360 degrees, which is our requirement. That is what is explained here. So the tank circuit will determine the frequency of oscillation. So if theoretically you adjust A beta equal to 1, then the circuit will provide sustained oscillations, sinusoidal oscillations in that particular frequency. So practically we have done this experiment. Hardly we have done it in our, I think Colpitts we have done it in our lab also. So there will be slight deviation if you measure theoretical and the practical frequency. It will not be exactly same. So practical frequency will be slightly either more than the designed frequency or it will be less than the design frequency because of various parameters, the power supply, because of your resistance values, because of the capacitor values, the transistor beta may not be high. So all these values will change the frequency of oscillation from that the theoretical value f naught to slightly more than f naught or slightly less than f naught. Okay. So this is the frequency of oscillation of general LC oscillators. So here the C will determine the equivalent capacitance. C1 and C2 are in series. So the equivalent capacitance C will be equal to C1 C2 by C1 C2. C1 C2 by C1 plus C2. And how they are in series, assume that if you have a current flow here, the same current flow will flow through C1, C2, 1L. The loop current, if you assume in this loop, the same current will flow through C1, C2, and same current is flowing through all the components. It can be understood that all the components are in series. So C1 and C2 are in series. So the effective equivalent capacitance is given by C equal to C1, C2 by C1 plus C2. There, in the Hartley oscillator, we found out that L1 and L2 are in series. So L will be equal to L1 plus L2 plus or minus 2m, which is the mutual inductance factor. So here we are going to find C equivalent, so which is going to be C1, C2 by C1 plus C2. So Hartley is widely used because I eliminate one inductor and in my circuit it has only one inductor. So Hartley I had two, but in Colpitts I made it one. So my circuit will become relatively smaller in size if I am going to eliminate the usage of inductors. And all LC oscillators are used only in high frequency applications. So it will work very good between 1 megahertz and 500 megahertz, which is a very high frequency. So those applications, wireless communication, so all those where this frequency I need oscillation, I can be using this Colpitts oscillator for such applications. So it is predominantly used in super heterodyne radio receiver. Okay, the application is super het radio receiver. So same way we are going to derive the frequency of oscillation. So Z1 is capacitance 1 by j omega C1 or minus j by omega C1. Z2 is 1 by j omega C2 or minus j by omega C2. And Z3 is inductor j omega L. So substitute all these things in generalized equation for LC oscillators. You will get this equation minus j HIE into 1 by omega C1 plus 1 by omega C2 minus omega L plus the real part equal to 0. So we have done all the derivation in the offline class. So we are just going to revise how we are going to get F naught and other things here. Okay. So if you equate the imaginary term to 0 and put omega equal to omega naught, you will get 1 by omega naught C1 plus 1 by omega naught C2 equal to omega naught L. So if you find omega naught L, omega naught will be equal to 1 by root of LC or F naught equal to 1 by 2 pi root of LC. And C is going to be C1, C2 by C1 plus C2. So this is the frequency of oscillation we get. And you can see F naught depends on C1, C2, L. It does not depend on any of the transistor values. We used HIE, we used HFE in the equivalent circuit, but see none of the transfer parameters are coming in the expression for F naught. It is purely decided by the reactive components, what you are going to add in the feedback path. And HFE is going to be C2 by C1. So the minimum gain for the transistor to produce sustained oscillation is going to be C2 by C1, and it can be more than this also. So it can be more than this also for getting better oscillations.